Welcome to this presentation about combining specialist marine surveys and technology to mitigate the impact of cargo loss and damage. I'm Jan Verdazing, and together with my colleague Dennis de Bruin, we'll be presenting today. BMT is a multidisciplinary design, engineering and consultancy company operating in the maritime domain. We work in environmental studies, including flood modeling, port and harbors, critical infrastructure, offshore oil and gas, offshore renewables, like wind and tidal power, defense, from aircraft carrier design, down to harbor patrol vessels and fireboats, all of ship design in the commercial domain, like ferries, crew boats, CTVs and other bespoke vessels, engineering support, and inspection and surveys. BMT has 47 offices around the world and employs around 1,500 experts. As an employee-owned company, we are truly independent and can therefore act in the best interest of our customers. BMT works with centers of excellence, and for today's presentation, our centers in Rotterdam and Singapore are presenting conjointly. I'd like now to hand over to my colleague Dennis, who will take you through the next part of this presentation.
BMT is a marine consultancy with over 1,200 specialists in numerous fields of marine expertise, and as such we can solve a large variety of complex marine problems by expert knowledge, experience and the use of BMT-designed in-house technology. The Marine Survey Division of BMT, with over 40 maritime experts, is dedicated to investigating marine casualties all over the world, and on behalf of anybody that experiences a maritime problem or dispute. This could, for instance, be an investigation into a collision or a container loss, but also in relation to cargo losses and contamination in oil and gas transport or bulk cargoes such as grain and coal. Additionally, we also render our services investigating hull damages and machinery breakdown, as well as fire investigations. Our clients traditionally include ship owners and/or operators or their insurers, law firms and cargo owners. Our BMT marine experts use many of the facilities that we have developed in the BMT group, and that obviously gives us the benefit of having access to advanced technologies that our competitors may have to buy in somewhere else in order to complete their investigations. Having these technologies within reach gives us a large flexibility and it reduces our costs. Whilst BMT is able to render services in a wide range of different fields of marine expertise, we will, for the sake of this presentation, take you along in our journey to the world of container loss investigations, during which we will explain on a high-level basis a bit of the approach to such an investigation, as well as the use of the technology that is available within BMT. During decades of container loss investigations, we have seen a massive increase in container losses. That is not only due to the size of the vessel, which is continuously growing almost beyond the imaginary, but it is also due to the fact that a number of incidents seem to increase. Where an ordinary container loss would include up to 50 or in extraordinary cases maybe 100 containers earlier this century, we now often see massive incidents, easily including 300 to 500 containers, and in exceptional events even over 2,000 containers. The seed of large overseas container shipping was planted in the mid-50s of the previous century, and as such we are looking at an evaluation in container transport spanning some 65 to 70 years. During that period, the carrying capacity of the vessels has been multiplied several times, and where container ships were able to carry up to 1,020 feet containers around 1960, the new built vessels that recently have been delivered can easily take up to a capacity of 24,000 20 feet containers, or TEUs, known as the 20 feet equivalent units. With plans on the table to increase intake capacities up to 30,000 TEUs, the limits to both building these ships as well as being able to navigate them have not yet been reached. The continuing competition to build larger vessels brings along another side effect, that of the container loss incidents. Bigger ships create bigger problems, and when containers are lost, we do see an increasing trend in the number of containers that are being lost in a single incident. Considering that containers have the ability to float for quite a considerable period, depending on their loaded condition, these incidents do bring all sorts of dangers to the marine environment and navigation, not to mention the volume of debris that will wash up on beaches when incidents occur at relatively close proximity to the nearest shore. The loss that many containers and their cargoes, as well as the damage to the environment, comes along with extremely high exposures on account of the underwriters who are faced with significant claims. You can imagine that a lot of those containers contain a lot of plastics, which will become microplastics if they are lost in the marine environment and be there for a while. We are taking you along into a real container incident in a short movie on the right side of this slide. When looking carefully, you will notice that a number of container rows show excessive movement, and some will eventually be lost overboard during the vessel's voyage in heavy weather. Generally, there are many causes that may lead to a loss of containers, and quite often there is more than just a single cause that contributes to the loss itself. However, the principal causes to a loss are often related to, firstly, the ship's motions, which can be quite excessive in heavy weather, sometimes due to hydrodynamic effects, and also due to parametric rolling incidents. Then we have the lashing and securing failures. That may often come with the application of the lashing and securing components, the design of the components itself, or the condition of the equipment used. Then there are stowage failures. We often see that the weight distribution in stacks is wrong, where heavy containers are stowed over light containers. Sometimes this is due to wrong terminal planning, but it can also be caused by a misdeclaration of the containers itself. Stowage failures often have a correlation with the vessel stability. Then we have the container itself. The condition, the size, and the declared weight are very important parameters in an investigation into a container loss. Our database of container incident investigations shows us large numbers of incidents in which incidents can be allocated to a stowage failure. For such an investigation, it is important to understand what forces are acting on the container whilst in transit on board a seagoing vessel. The most important forces are the stacking weight, which is a gravity force, and that comes along with the weight of the cargo inside the container. Then we have acceleration forces under influence of the vessel's rolling and pitching motions. That rolling and pitching motions may bring acceleration forces in various directions is perhaps not too difficult to understand. Slamming, and predominantly aft body slamming, has been recognized as a contributing factor to increased acceleration forces. This effect came with the changes in ship's design, which increased the uplift forces on the aft part of the vessel due to the vessel's aft part slamming on the water surface. This slamming effect is best illustrated by two pictures at the top of this slide, which shows the design changes to the aft body of the container ships before 2000, which basically looked like a knife-shaped aft ship, and after 2000, when ships were more and more designed to accommodate as many containers as practically possible. Then there are forces acting on the container stow from the outside. These are often caused by wind and sea, like wind forces and sea forces by seas taken over on the main deck. When taking into account the above mentioned forces acting on the container stow, there are four main forces acting on the containers and their lashing equipment in seagoing motions. These are, firstly, the tension, or known as uplift forces, which are forces acting on a container stack trying to lift the container from the vessel's deck. Therefore, they are often referred to as uplift forces. Compression forces are the second, which are acting on the container stack trying to compress it towards the ship's deck. Then we have racking forces acting on the container in a sideways direction, attempting to reshape the box-shaped model of the container in some sort of a parallelogram. And the fourth force is the shear forces, acting on the container from the outside under the influence of wind, trying to push the container stack aside. In the combination of container weights, sizes, and stowage position on board the vessel are the input parameters to assess the lashing forces, calculated by the ship's loading computer. This is important information when performing the lashing force calculations, for which we use class-approved software applications and a team of experts who are trained to work with the models and to interpret the output parameters. The illustration to the right is an example of the output of such a calculation. The correct use of these systems require modeling of the vessel's dimension, stability, and maximum motions according to the design criteria. With this model, the output gives an evaluation of forces acting on the individual container stacks. In this example, calculations of a certain ship indicate that row 9 in a nominated container bay was subject to high compression forces. That is seen by the red flags in the calculation model. This is highly likely to have had an impact on the condition of the container in that particular area, and that can be confirmed by onboard inspections of our team of experts who are able to travel to any port worldwide. One of the most common problems causing container losses traditionally was the misdeclaration of the container weights, as already mentioned earlier. Shippers of any type of good carried in containers are obliged to notify the carrier or the bill of lading party about the correct weight of the container that they present to the vessel. This is essential information that is taken up into a terminal planning system that allocates this container a predefined slot on board the ship. Weight and size of the container are of utmost importance, as heavy containers cannot be stowed in high stowage positions, such to avoid excessive lashing forces en route. The issue of misdeclaration has been taken up into the IMO, which regulates that container weights need to be verified and certified by a verified gross mass certificate. That is handed over to the carrier. Although the idea behind that system is quite solid, we still come across situations in which the declared VDM weight doesn't match the actual container weight, and that increases the risk of container collapse incidents. That also applies to planning mistakes when containers with correct VDMs are simply placed in the wrong stowage position. All these elements need to be carefully evaluated from calculations and onboard inspections. Onboard inspections by our experts will provide us with essential information in order to help us to understand what the potential causes of a stack collapse might have been. In the next slides, we have illustrated a few examples. On the left side of the slide is an illustration of a wrecking force type of damage, which will explain itself by containers showing, for instance, broken door hinges and closing bars, and if the forces are extreme, further into broken door sills and total deformation of the original shape of the container into some sort of a parallelogram. The right part of this slide indicates a typical but strong compression force type of damage, which may be recognized by container corner posts that have been hammered on for a while, turning them into some sort of an harmonica shape. On the left side of this slide is an example of an excessive tension or uplift force. This usually explains itself by, for instance, broken lashing gear like twist locks and lashing bars, and broken container sills. It is important to perform this onboard investigation, as it will provide us an indication on where to find the causation of these collapses. I just mentioned one of the most essential pieces of equipment that would be necessary to make the ocean adventure a real success, and that obviously is the lashing gear. On a normal type of container vessel, this lashing gear would include twist locks to interconnect the container corners with the containers stowed beneath and above, as well as lashing bars, which are connected to at least 2 tiers of containers. Nowadays, ships are often fitted with lashing bridges in between different container bays. These bridges allow for a connection of the lashing bars at the 3rd or 4th tier, sometimes, depending on the size of the vessel, even up to a 5th tier of containers. This higher securing of containers to lashing bridges obviously allows for higher stacks on board the vessel and therewith higher intake capacities. Higher stacks will also increase lashing forces overall, and that can only be assessed by skilled experts using the right equipment. Most, if not all, container losses are initially allocated to poor weather conditions and ships laboring motions. Whilst that was an argument that was difficult to repudiate in the past, nowadays weather forecasting, and hindcasting if you like, allows us to assess the condition that a vessel actually met at the reported time of the incident. Within BMT, we do use our own Metocean forecast models, which are evaluated by environmental experts and oceanographers to conclude the real conditions that a vessel had met. That information is vital in our lashing force assessments and review of the stowage instructions on board a ship, as it has often been seen that vessels have been exposed to atmospheric conditions which are outside the design parameters. If that happens, this would impact the maximum tolerances on weight and forces. When container incidents either collapse of containers or navigational issues may have been caused by external events, such as, for instance, grounding and collisions, BMT is able to reconstruct the incident by using our BMT REMBRANDT simulation and reconstruction software. This will not only help us to understand the event leading up to an incident, but it also assists us in further elaboration on what could have been done to avoid such an incident. This is another obvious benefit that the BMT survey team has compared to its competitors.
Thank you, Dennis. I'd like to expand a little on the benefits of REMBRANDT, especially in the light of the accident investigations. REMBRANDT is a class-certified simulator scalable from full bridge simulator class A, B, C, or S, so basically all the different functions, down to a desktop or laptop version, which is able to be taken on board to run on a vessel independently. For accident investigation, the important part is that REMBRANDT is able to simulate a wide range of conditions, including visibility, wind and current, multidirectional swells, and dynamic current flows. This data can either be set in the program itself or being imported from Metocean data during the time of under investigation. As BMT operates in the environmental domain, we have access to both historical and current Metocean data, which makes the modeling way more accurate. For the vessel interaction, REMBRANDT can plug into AAS data directly from the source, allowing real-time display of live traffic as part of the simulation. Last but not least, as a ship designer, BMT has built up a large database of hydrodynamic models for many vessels which have been validated using sea trial data and can model the 6 degrees of freedom hydrodynamic model for the vessels in the investigation in-house. These models include physical phenomena like squat, bank effect, ship-to-ship operations, and ship-to-shore interactions. Dennis mentioned before the collapse of container stacks is often related to weather-related conditions and the behavior of the ship in these conditions. With REMBRANDT, we can do a step-by-step replay what happened in the time leading up to the accident. Our experience as ship designers gives us the knowledge to see how the ship structure is reacting to certain loading scenarios, resulting in a deep understanding of all factors contributing to the accident. From an accident prevention perspective, the combination of navigational simulator with the accurate Metocean data and weather prediction will give the vessel operator a chance to plan the vessel route to avoid any weather-related issues, avoiding container collapse due to rolling, for instance. The combination of all these insights we mentioned before, whether it's the weather risk, currents, vessel traffic, infrastructure interaction, and so on, can be used to develop a risk profile on vessel operations. This can be used by port authorities to put in place mitigations like traffic channels, tug requirement, pilot training, and so on. This will de-risk the maritime operations and lower the chance of accidents. Should, however, an accident happen due to either a misdeclaration of container weight we talked before or any other factors, I hope we gave you a good insight on how to approach an investigation and what tools to use to get the root cause quickly in order to finalize the recovery and the insurance process as quick as we can. I'd like to thank you for your attention and hope to speak to you soon.